strengths of acids and bases. In Gen Chem, you guys talked about strong acids, strong bases, weak bases. We often use those terms a little bit differently in organic chemistry. In Gen Chem, you defined a strong acid as one that was completely dissociated. Hydrochloric acid was considered to be a strong acid because you take hydrochloric acid in water, what you have are essentially zero hydrochloric acid molecules at that point. Essentially 100% of them have dissociated into hydrogen ions and chloride ions. That's the definition of a strong acid, complete dissociation. That is officially what a strong acid is, something that is completely dissociated. By that definition, however, there's virtually no such thing as a strong organic acid or a strong organic base. They don't completely dissociate. They don't reach the level of a hydrochloric acid or a sulfuric acid or a nitric acid or whatever other strong acid you're asked to cram in your head in your Gen Chem class. But some organic acids can be stronger than others. So when an organic chemist points to an organic acid and says that's a strong organic acid, they don't mean strong in the completely dissociated sense. They mean stronger than most others. They mean it in a relative sense. Sorry, that's just life. I'm the messenger. Okay, so let's talk a little bit about strengths of acids and bases. How do we measure it? Okay, pH can measure it. That essentially the pH, POH concept kind of requires we're talking Arrhenius. Kind of more generally, a Ka can tell us how strong an acid is. Here's a trick question for you. What's the Ka of, say, hydrochloric acid? You know, a typical strong acid that you talked about in Gen Chem. Your hint was, that's a trick question. Okay. How do we calculate Ka? What is Ka? Okay. More generally, K. Yeah, if you have any sort of reaction, you know, say A plus 2B gives C as an example of a reaction, the equilibrium constant is equal to the concentration of products raised to powers equal to their stoichiometric coefficients divided by the concentration of reactants raised to powers equal to their stoichiometric coefficients. That's the equilibrium constant in general. If we put a subscript A after that, how does that make it different? It doesn't make it different at all. It just is specifying that we're talking about something functioning as an acid. Okay, the A simply stands for acid. K can be for any reaction whatsoever. Okay, we're talking about a strong acid such as hydrochloric acid completely dissociates. What's its equilibrium constant? I've seen a 1, I heard a 0. No. What's kind of the opposite of 0?
Infinity.
Excuse me?
Infinity.
Infinity. It's going to approach infinity. If we have HCl it's going to completely dissociate. So all of it goes here, there's going to be none of it here, denominator approaches 0, the quotient approaches infinity. It's essentially infinity for a strong acid in the classic Gen Chem sense. Okay, so we're not going to deal with any acids that have Kas that approach infinity. They're going to be actual numbers. What can be said about the Ka for an organic acid that is relatively strong? Ka will be, one word answer will suffice here, large. For a weak organic acid, Ka will be small. So we know about Kas, he says, perhaps too optimistically. And we know about pKa. What's pKa? Okay, maybe you're not familiar with pKa, but you can't sit there and tell me you're not familiar with pH. What's pH? Okay, it's not, the concentration of hydrogen ions is a part of pH. The logarithm is a part. We need one additional thing.
Oh, negative.
The negative, exactly. pH, I know you know this, is the negative log of the proton concentration. That's pH. So P is a mathematical operator like any other mathematical operator. It simply means take the negative log of whatever. So pKa is the negative log of the Ka. So if we're dealing with a strong organic acid, which again doesn't mean one that's completely dissociated, but one that's more dissociated than most, if we're dealing with a relatively strong organic acid, pKa will be, one word answer, small. If the Ka is large, that means significantly to the right the reaction lies. If the Ka is large, the log of the Ka will be large, the negative of that will be small. And if we're dealing with a weak organic acid, Ka will be small, pKa will therefore be relatively large. So we can use Ka and pKa to measure how strong or not strong an organic acid is. Okay, as far as determining who's a strong acid or who's stronger than who, let's just look at some comparisons and talk about them. If we look at hydrogen chloride versus hydrogen fluoride, which of these is a stronger acid? Hydrogen chloride is the strong acid. I mean, it's strong in the traditional sense, complete dissociation. Hydrogen fluoride was probably an example acid you used in Gen Chem of a weak acid that doesn't completely dissociate. So in terms of acid strength, hydrogen chloride is more acidic than hydrogen fluoride. Why? Chlorine? Huh? Fluorine. They're in the same group, but they're in different. Jenny, you gonna say something? But you just. Yeah, it's all about size. It's all about size. To talk about these guys as acids, we're talking about their ability to get rid of the hydrogen as a cation, to donate H+. The hydrogen here, because Chlorine is a relatively big atom. Fluorine, a much smaller atom. Remember, when you go from one period to the next, the size difference is very substantial. So we got hydrogen here. There's the positively charged nucleus that's holding it in place. We've got hydrogen here. There's the positively charged nucleus that's holding it in place. This hydrogen is able to get a whole lot closer to the positively charged nucleus here, so it's held onto much more tightly. To say that it's held onto much more tightly is to say that it isn't released as readily, which is to say it's less acidic. So size very much matters. But please appreciate, size matters only in terms of the atom that the hydrogen is bonded to. You know, if we have hydrogen bonded, say, atom X, you know, and X is going to be bonded to some guys Y and Z, you know, it doesn't matter how big these guys are, totally irrelevant. It only matters the size of the atom that the hydrogen is actually covalently bonded to. Rock and roll? How about hydrogen fluoride and water? In hydrogen fluoride, we have a hydrogen covalently bonded to fluorine. In water, the hydrogen is covalently bonded to oxygen. HF is the stronger acid. Exactamundo. Pourquoi?
Because you have two H's on the oxygen, so it's not as strong, even though it's to the left, it's equal by two.
Well, actually, the fact that there are two is not particularly important. I mean, what you're saying is correct, but that's not the biggest issue here. The main reason why there are two is simply that oxygen is capable of forming two bonds. Fluorine is only capable of one.
Is the hydrogen bonding with the other hydrogen?
Okay, that's the fact. First of all, both of these are capable of hydrogen bonding. So that's not really a distinguishing factor, though that's kind of relevant.
Is it because there's more protons and more electrons closer, so it makes it smaller?
Okay, I wouldn't necessarily, yeah, I guess it's kind of the more proton thing. Give me the magic word there. You pretty much described it, but there's a magic word that we all know. First of all, is it going to be a size factor like it was between HCl and HF? Is it going to be a size factor? Electronegativity is the magic word, which is basically what you described. It's not going to be a size factor. It was a size factor here because we're in different periods. Guys in different periods have radically different sizes. It's not a size factor here because we're in the same period. Yes, there's going to be a size difference, but it's minor. The much more significant difference is electronegativity. Fluorine is more electronegative than is oxygen. So the shared pair of electrons, fluorine is sucking those pair of electrons closer to it than oxygen is. Sucking this pair of electrons towards itself is enabling this bond to break heterolytically more readily, which is what has to happen for it to function as an acid. So it's all about electronegativity. Well, when is size the issue, and when is electronegativity the issue? Size is almost always the most important consideration if the two compounds we're comparing, the hydrogen is bonded to guys in different periods. Electronegativity is almost always the dominant issue if the two atoms that hydrogen is bonded to are in the same period. In other words, size trumps electronegativity if there's a meaningful size difference. There won't be a meaningful size difference if we're talking about guys in the same period. Okay, how about there's a hydrogen bonded to carbon. First of all, in general terms, is that going to be an acidic hydrogen typically? No. They have very similar electronegativities. In order for this bond to break heterolytically, the carbon has to hog the pair of electrons. He doesn't particularly want to hog the pair of electrons away from a hydrogen. Very similar electronegativities. But let's compare this carbon-hydrogen bond to this carbon-hydrogen bond, where here his other three bonds are all to hydrogen. This guy's other three bonds, I say all to fluorine. Which of these is going to be the stronger acid? First of all, neither one is going to be a kick butt acid because we're talking about hydrogen bonded to a carbon. That will never be what anyone would call a strong acid. But there is a very distinct difference in strength between these two. The stronger one is this one. Again, to talk about these things functioning as an acid, we need this bond to break heterolytically, where the pair of electrons remains with the carbon, and he leaves without that pair of electrons, i.e. donates a proton. Well, we're bonded to carbon in both cases, but fluorine, being highly electronegative, is sucking electron density its way. So the fluorines are sucking electron density away from this carbon, giving this carbon a partial positive charge, so he's going to suck this pair of electrons towards him. Whereas there's nothing giving this carbon any sort of partial positive charge. So everything is very non-polar here, but there's some induced polarity here. The electronegative fluorine sucking electron density its way. Does it matter how big this fluorine is? Not at all. Size only matters if we're talking about the atom that the hydrogen is actually covalently bonded to. It matters how electronegative this atom is. The more electronegative it is, the more it's sucking electron density its way, effectively away from the hydrogen, so the hydrogen can be donated as a proton. Okay. That should all be reasonable, he says optimistically. Here's a potentially acidic hydrogen, here's a potentially acidic hydrogen, here's a potentially acidic hydrogen. In each case, we've got hydrogen bonded to carbon. In none of these cases do we have anything other than a hydrogen or a carbon. Are any of these guys going to be particularly acidic? No. There's pretty much no such thing as a hydrocarbon that's particularly acidic. But there is a distinct acidity difference here. Anyone want to guess? Maybe it is this time. Which of these is the most acidic? The alkyne, the alkene, or the alkane? The alkyne is the most acidic. The alkane is the least acidic. And the reason is this. What's the orbital hybridization of this carbon? sp3. An sp3 hybrid is 3/4 p-like and 1/4 s-like. So an sp3 hybrid orbital kind of looks like this. There's a little irrelevant lobe on the other side. You know, a flat out P, of course, is evenly bilobed. He's going to have a lobe, doesn't stick out quite as much as a P, because it's 1/4 S, as opposed to an sp2, which is going to stick out even less, because it's only 2/3 P, 1/3 S, as opposed to an sp, which is half S, half P. So the pair of electrons that's being shared with hydrogen, hydrogen brings a 1s orbital to this, of course, that's all he's ever got. This pair of electrons is closer to the nucleus if that carbon is sp hybridized than it is to the nucleus if the carbon is, say, sp3 hybridized. In effect, an sp hybridized carbon is more electronegative. Electronegativity is all about sucking electron density its way in a bond. The sp hybrid orbital pulls that pair of electrons closer to the nucleus. In effect, an sp hybridized carbon is more electronegative than an sp2 hybridized carbon is, which is more electronegative than an sp3 hybridized carbon. So this hydrogen bonded to an sp hybridized carbon, is actually fairly acidic. Not mega acidic, not a whole lot acidic, but acidic enough to be meaningful. Rock and roll? Okay. One other thing to say about this. Of the list of organic functional groups we gave the other day, which is the most acidic? Carboxylic acids. That is why we call them carboxylic acids, because they're relatively acidic. So carboxylic acids, as everybody clearly knows, look like that. So for this guy to function as an acid, he's releasing a proton, and what's left over as he releases a proton is the anion, like any other acid. Donate H plus, and anion is left over, assuming the acid was neutral to begin with. This, of course, is a carboxylic acid. This is a carboxylate ion. If you think back on Gen Chem, you should be comfortable with the ATE suffix being indicative of an anion. I'm sure you talked about nitrate, sulfate, phosphate. All those guys are anions. So change the ic acid to 8. Basically means you got an anion. The way you have an anion is you donate a proton. So after having donated a proton, we've got the carboxylate anion. Okay, so this is acidic. It's substantially more acidic than, say, water. And I mention that because our acidic hydrogen is bonded to an oxygen. In water, the hydrogen is bonded to an oxygen. So comparing this to water, the hydrogen are bonded to guys of obviously the same size. Same electronegativity because it's the same atom. There is a bit of an inductive effect here in that I have a second oxygen, which is sucking electron density its way, and therefore effectively away from this hydrogen, making it a little bit more easy to release. So we can explain the greater acidity of this compared to water in terms of the inductive effect, but there is a far more substantial explanation. And we need a far more substantial explanation because this is way more acidic than water. Its increased acidity compared to water simply can't be explained by the inductive effect. Anybody got an explanation for why carboxylic acids are substantially acidic? I do. Drawing all the non-bonding electron pairs in this guy. There's a carboxylate anion. What's the difference between these two oxygens? It looks like I have a -1 formal charge on this guy, no formal charge on this guy. But that's wrong. What's the difference between these two bonds? It looks like this oxygen is pi bonded to the carbon and this one isn't. But that's wrong. There's another magic word. Resonance. 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 I can draw an alternative resonance structure here. I can take one of these non-bonding pairs. When drawing resonance structures, you can move non-bonding pairs around. I can move one of those non-bonding pairs down and make a double bond here, and I can take one of these pi electrons and move it up there. In addition to non-bonding pairs, you can move pi electrons. Do not ever move anybody else. If you move any sigma bonded electrons, what have you done? You've broken that bond. You're carrying out a chemical reaction now. That's not what we want to do. We're simply describing the carboxylate anion. So by following these arrows, I can draw that alternative resonance structure for the carboxylate anion. Which of these is the real carboxylate anion? Neither. What is the real carboxylate anion? A hybrid of these two, something intermediate between them. So what is the charge on this oxygen? -1/2. What is the charge on this oxygen? -1/2. What is this bond, single or double? Neither, it's like a 1.5 bond. What is this bond? It's like a 1.5 bond. That's the whole idea behind resonance hybrids. This isn't it. This is ugly dad. This isn't it. This is beautiful mom. The real carboxylate is somewhere in between. In other words, there's no atom here that has a full charge. Generally speaking, ions are less stable than neutral molecules precisely because they have a charge. Anything that has a charge is going to be fairly reactive. If you're negatively charged, you're on the hunt for positively charged things. You want to react with something positively charged. As a general rule, ions are simply less stable than neutral molecules are. But an ion where no atom actually has a full charge is going to be substantially more stable than otherwise, compared to, say, an ion where an atom does have a full charge. Alcohols, for example. Because we have hydrogen bonded to a highly electronegative atom, they are reasonably acidic. They can donate a proton, and we're left with something called an alkoxide ion. You know, this happens. We have hydrogen bonded to a highly electronegative element. This happens, but it doesn't happen near as much as this happens, because in this ion, there's nobody that has a full charge. Therefore, this ion is relatively stable as ions go. This ion, this oxygen, has the full negative charge. There are no alternative resonance structures we can draw for this thing. So this ion is substantially less stable than this ion. Therefore, it's less likely to form, which means this is less likely to do this reaction, which is to say this is less likely to be acidic. Okay, this is very important. Am I conveying the fact that it's very important? I believe I am. Any reaction that produces a resonance stabilizable species is going to occur to a greater extent than if you're producing a non-resonance stabilizable species. This is why we call these things carboxylic acids. This is why they're substantially acidic, because we produce a resonance stabilizable anion. Coolio. Coolio. Yo, Wentima. I'm done with chapter 3 as far as I'm concerned. We got 15 minutes left. Should we do the quiz now? No. I'll have a group quiz tomorrow and the individual quiz on Thursday. But I'm not going to waste 15 minutes. We're going to move on to chapter 4 stuff, which will not be on Thursday's quiz. Okay, the first 3 chapters, what we've done thus far is largely kind of a review of Gen Chem stuff, okay? You know, some slightly different applications, you know, some new stuff tossed in, but largely a review of Gen Chem stuff. Starting now, until middle of June when we're done, it'll be all new stuff. Yay. Let's start with talking about nomenclature a little bit. You guys did some nomenclature in Gen Chem. NaCl, sodium chloride you learned. Good for you. Nomenclature is important with inorganic compounds. You know, we're not going to be able to keep track of the approximately 150, 250, I don't know, 200,000, give or take 100,000. I don't know exactly how many there are inorganic compounds without some sort of systematic way of naming them. If that makes sense to you, how about trying to keep track of the 15 million, give or take a few million, organic compounds that are known? Being systematic about nomenclature is way more important in organic chemistry than any other branch of chemistry, because of just the wide variety of stuff. So, we need to talk about nomenclature. We'll open up with the alkanes. They're the simplest guys. The first thing we need to do is memorize some names. It's going to be easy, he says optimistically. The 1 carbon alkane is called what? Anybody know? Of course you do. This is methane. If you didn't know it prior to today, you know it now. you will never forget it till the day you die, and maybe not even after that, who knows. The 2-carbon alkane is ethane. The 3-carbon guy is propane. The 4-carbon guy is butane. The 5-carbon guy is pentane. The 6-carbon guy is hexane. The 7-carbon guy is heptane. The 8-carbon guy, octane. You know, most of these prefixes are probably familiar to you. They're used in lots of different contexts. Hept means 7, hex means 6, pent means 5. The prefix used for 9 might be new to you. The 9-carbon guy is no name. The 10-carbon guy, logical, should be decane. We can keep going, but we won't. That's enough. So you have 20 seconds in which to memorize those. Okay. Now, just because I wrote these in this shorthand, it is important to appreciate that here heptane is 7 carbons all in a row. We of course could have isomers of heptane that has 7 carbons, but not all lined up in a row. But the name heptane applies to 7 carbons all in a row. Okay, so that's easy enough. What if we do have not all in a row? Suppose we have this compound. The rule is, and these folks make the rules. You've probably been exposed to UPAC before. It stands for the International Union of Pure and Applied Chemistry. I don't care that you know that. It's basically an international body that decides things, such as how should we name the compounds. We could sit down and come up with a different system that might be just as logical as the UPAC system. Good for us. We could talk to each other. We couldn't talk to anyone else on the planet. So if you want to be able to talk to anyone else on the planet, you need to use the UPAC system of nomenclature. Okay, so rather than kind of give you rules, we'll just go through examples. The most important thing that UPAC says when naming a compound that isn't just a straight chain is find the longest straight chain. So in this compound, the longest straight chain contains how many carbons? 3. That would be propane. Is this propane? Of course not. Propane is just 3 carbons all in a row. Propane is, if you will, the backbone of this compound. What is stuck onto that propane? There's 1 carbon stuck on. 1 carbon is methane. But we give the name methane if that 1 carbon is all by itself. It's not all by itself. The 1 carbon is stuck onto something else. So we drop the A and E and add YL. This is therefore methyl propane. UPAC says that should be all one word, methyl propane. There is kind of a human tendency to want to make it 2 words, methyl space propane. If you make it 2 words, you will earn all the points for that question, so don't worry about it. If I feel like you're doing kind of too much of that, I might try and draw a little connector to encourage you to make it 1 word. But don't get hung up on that, it's not important. Okay. So who's this? This is just butane. Done. It's It's 4 carbons in a row. Don't let me fake you out like this. I'm not drawing them all horizontally, because I will try to fake you out with this. You will have compounds on the first quiz that are not drawn all in a row. But this is 4 carbons in a row, so it's just butane. Who's this? The longest continuous chain? 5 carbons, that makes it pentane. Is anything stuck on that 5 carbon chain? 1 carbon is, that's a methyl group, that makes it methylpentane. Who's this?
Same. Methylpentane.
Oh, it's a 3-methylpentane.
The longest continuous carbon chain is 5 carbons, that makes it pentane. There's a 1 carbon guy stuck on, that makes it methylpentane. Are these the same compound? No.
The third carbon's 3-methylpentane.
Exactly. What is the relationship of these 2 compounds to each other?
Same carbons, they're same written, same structure, well, not structure,
constitutional
written
isomers.
CH. You know, they're written the same.
Yeah,
Same formula.
Same molecular formula,
Constitutional
so that makes them
isomers.
isomers.
Isomers,
They're constitutional isomers of each other. They're different compounds, they therefore have to have different names. As Jonathan indicated, what we do here, what UPAC says we do, is we number the parent chain. So here's carbon 1, here's carbon 2, here's carbon 3, here's carbon 4, here's carbon 5. In this one, the methyl group is on carbon 2, so we call this 2-methylpentane. In UPAC nomenclature, there's always a dash between a number and a letter. If you put something other than a dash between a number and a letter, you will still get 100% of the points for that question. But I will circle your comma or apostrophe or whatever weird mark you put here and try and make you feel a little guilty for putting something other than a dash. I won't take points away from you though. It should be a dash between numbers and letters. If this is 2-methylpentane, this logically is 3-methylpentane. And this logically is,
2-methylpentane.
it's 2-methylpentane
Left to
autrefois.
right, right to left.
This is the same as this. This is also 2-methylpentane. These are the same compound. All I do is take this and flip it over. The UPAC rule is we number our parent chain starting at whichever end puts the substituent on the lowest numbered carbon possible. So I would choose to start numbering from this end because it puts the methyl group on carbon 2. Had I started numbering from this end, it would put the methyl group on carbon 4, as a number of you said. There is no such thing as 4-methylpentane. 4-methylpentane is just a incorrect name for 2-methylpentane. Always start numbering from the end of the chain that puts the substituent on the lowest numbered carbons possible. So who is this? What's my parent compound here?
Butane, 2-methylbutane.
Incorrect.
3-propylbutane. 3-propylbutane.
No. What's my longest
2.
continuous chain?
3.
Incorrect. Incorrect.
They're the same.
5. There's my longest continuous chain. Just because I didn't draw it horizontally, that is extremely irrelevant. Those 5 carbons are all in a row, so that makes this a pentane. Got a methyl group stuck on this sucker, and it's on carbon 3. In other words, these 2 compounds are the same. I just drew them differently, but they're the exact same compound. Who's this? My longest continuing chain is 8 guys. That makes it an octane. Who's stuck on?
There's a methyl and a
2-methyl.
I've got a methyl group stuck on, and I've got a 2-carbon thing stuck on by itself. That's ethane. Drop the A and E, add YL. As it's stuck on to something else, that makes this an ethyl group. So I have a methyl and an ethyl stuck on. UPAC says if there's more than one substituent, we alphabetize them. So I should put the ethyl before the methyl.
and up for each one.
If you do it the other way, if you put the methyl before the ethyl, you will get full credit. So don't get hung up on that. But you should know, here I am telling you, UPAC says we should alphabetize. And yes, we have to specify where they are. The methyl group is on carbon 2. The ethyl group is on carbon 5. Yeah, some of you are going to want to say, well, we're on carbon 2. This guy, if I start numbering from this end, 1, 2, 3, 4, that's a lower number than if I start here, 5. You can't switch ends. You have to start numbering from one end and stick with that. So you choose the end that collectively gives the lower numbers. Going from this end, I have 2 and 5. Going from this end, I have 4 and 7. 2 and 5 are lower numbers than 4 and 7. Therefore, I start from this end. Okay, one other thing to say before I let you go. On the second lab that you'll be starting, it's a microscale lab. Just a word of warning, being careful matters a whole lot more when you start with not much stuff to begin with. So be careful, ask questions as needed. The best way typically to dispense volumes that are small, like sub-milliliter volumes, on the microliter level, is with one of these things, a micropipette. My guess is some of you have played with micropipettes and some of you have not. You'll figure them out. There's nothing complicated about it. We'll help you. I'll help you. Gina will help you. Somebody will help you. Don't worry about it. If you've never seen one of these things. There are tips that go on the end. We have different sizes. Put the right size tip on. It'll be obvious if you're trying to put the wrong size tip on. Either it won't fit or it'll be on there kind of loose. But don't freak out if this tip doesn't fit, probably because you have the wrong size tip. And only 2 things I want to say about these guys. When you push this button down, there's a point of resistance. The way you work these things is you have to set it to the desired volume, and we have different makes that are slightly different. So you'll figure it out, or you'll ask somebody how your particular micropipette works. But you set it to the desired volume. You push the button down to the point of resistance. Stick it in the liquid you want. Suck that liquid up. Move it over to where you want to dispense that liquid. Push the plunger back down, and then push it beyond that point of resistance. That gives it a little to get all the liquid out of this tube. That's how they're calibrated. Push it down to the point of resistance, suck up the liquid, wherever you want to dispense it, push it further beyond that point of resistance. Now the second thing I want to say, and this is very important, do not ever do this. These things clog up a lot, they get gummed up, they're constantly malfunctioning, and 99% of the time they malfunction because somebody sucked up some liquid and was talking to somebody and is doing this. I mean, there's kind of a tendency to want to do this. You suck up some liquid, you don't want it to drain out the tip. Oh, I do this, it won't drain out the tip. Well, it's going to drain into the works of this thing and gum it up. So, I mean, if you don't have any liquid in here, do whatever you want with it. If you have liquid in here, keep it vertical.